Okay, so basically now that we know derivatives, we're able to use L'Hopital's rule on limits. You're going to watch this and think, why didn't we just learn this the first time? Because we didn't know anything about derivatives yet. So this technique, if we look at some of the things we did, for example, this one here, we had these fancy techniques. Do you remember what we did on this? Maybe, yeah? How did you deal with that limit? Factored it, right? So it would have been like 2x squared minus 1 over x plus 1, and then 2x plus 1, x minus 1, and then x plus 1. So that would remove the discontinuity, and I would just be thinking about 2x minus 1. So I could find that limit now through direct substitution. Okay, and then do you remember what was the technique when we dealt with these infinite limits like this?
Bill Gates math?
Yeah, the Bill Gates math, right? What is it finding here? If we're looking at the limit towards infinity, what is it doing for us? There's a feature it's helping us find. I just want to jog your memory about that. Horizontal asymptotes. So part of curve sketching that we've talked about in this unit was the main features. So vertical asymptotes, horizontal asymptotes, critical points, and inflection points, all those things that can help you sketch. So in this instance, yeah, we're looking for horizontal asymptote. What's the value going to be? Yeah, 3 over 2. So again, I don't know why every year I teach this, people have a hard time with it, but if you have billions of dollars and someone takes away 1, it's not a big deal. So these things here, they're not significant. Really what we're trying to think about is only the most significant terms, because for very big numbers, that's really all we're looking at is that. So the asymptote's going to be at 3/2. Now, we call these indeterminate forms, and the only rule for L'Hopital's rule, too many rules, I guess, is that you have to use it on indeterminate forms. So what do they look like? If you were to substitute into this first example, what you get is 2 times negative 1 squared. Sorry, I'm sticky pen here. Squared minus 2 divided by negative 1 plus 1. So the first example, if I did this, would be 2 minus 2 over negative 1 plus 1, which is 0 over 0. So remember I told you that's interesting. You have to dig deeper when you run into 0 divided by 0. The technical word for it is an indeterminate form. It means we can't determine whether or not that's the end of this limit or not. We're not able to know yet, so it's indeterminate. We have to do some more stuff to it. The one over here, when you substitute it, you'd have, I don't know if this even really makes sense, 3 times infinity squared minus 1, 2 times infinity squared plus 1. So we're going to have infinity over infinity, right? And again, we don't know which one wins, so we'd have to do some more math to figure it out, so it's indeterminate. But those are the main forms of L'Hopital's rule that we're going to be looking at, is how do we deal with limits when we run into 0 over 0 and infinity over infinity. So what about when we run into something like this guy? Anybody think you can come up with a technique here? It's tough because the algebra there is it's not as cookbook. It's ready to go and it works in these indeterminate forms. There's lots of indeterminate forms that we haven't learned how to deal with. So first, let's go take a look at the picture and see if we can use that to give us some sense whether the limit exists and what it might be. Okay, so it'll be e to the 2x minus 1 divided by x. And we're looking for it at 0, so that's what I'm going to make my window close to. Maybe we'll go from negative 2 to 2. And I don't think I could zoom out later. I don't think I need to go that high, so I'll try and shrink it a little bit. But again, you can always zoom in on it with your, you don't have to set your window at the beginning, but. So according to the limit, if we were to look at this and try and substitute, here's what would happen. We would plug our numbers in, and we would get e to the 0 minus 1 over 0. 1 minus 1 over 0. This is a 0 over 0 situation. So we don't know exactly what's going on, but then we look at the picture here, and it doesn't look so bad. It looks like there must be a limit here at 0. It's nothing crazy is happening. I can approach from the left. I can approach from the right. It looks like it's well behaved. So let's try and put in what we've got here. Something like this. So if we had to estimate it, maybe I'll trace it just to get a better value here. So it's very close to 2 on the right-hand side. So I'm a little bit bigger. From the right-hand side, it's a little more than 2. And it's a little less than 2 on this. So I'm going to guess that it's 2. I don't know if that's right, but let's guess that it's 2. So here's the way L'Hopital's rule works. It's nice and simple. If you do have one of these indeterminate forms, the limit as x goes to 0 of f of x over g of x is equal to the, oops, sorry, it doesn't have to be a 0, it could be anything, right? Limit as x goes to a is the same as their derivatives. So what we're going to do to cut this limit down is we're going to take the derivatives and that hopefully reduce how complicated the limit looks. So let's take a look at this limit as x goes to 0 of e to the 2x minus 1 over x. This is not doing the derivative with quotient rule. This is the derivative of the top divided by the derivative of the bottom. Nice and simple. So the derivative of the top is going to be 2 e to the 2x, while the derivative of the bottom is 1. Now I have to stop and decide, can I apply the limit? If I can't, maybe I need to apply L'Hopital's rule again or try one of my techniques. But the problem before was in the division by 0. It is now gone. So let's just see if I can plug it in. That would be 2 times e to the 0 over 1. So 2 times 1 over 1, that's 2. So a little bit of magic happens, and we do have a limit there of 2. Let's go take a look at what we would have had on those previous ones. If I take a look at this one here, let's take a look at the derivative of the top divided by the derivative of the bottom. So derivative of the top would be 4x. Derivative of the bottom would be 1. There is no more discontinuity. I'd be able to just directly substitute it in. So I would have negative 4, which if I put it in here, it would have been 2 times negative 1 minus 1. So 2 times negative 2, which is negative 4. I think you'll all agree that L'Hopital's rule is much quicker. It's also much more versatile because the one rule has worked here. It has worked here. Let's try this one as well. 3x squared minus 1 would become 6x over 2x squared plus 1 would be 4x. So this time I'd have the limit as x goes to infinity of much simpler expression, which is just 6 over 4 because these would divide out. And we could also call 6 over 4 3 out of 2. Okay. You could apply L'Hopital's rule a second time to this. If you overthink it and you don't divide your x's out, you have 6x over 4x. If I put in the value, this is infinity over infinity, so L'Hopital's rule does apply again. The derivative of the top is 6, the derivative of the bottom is 4, and now there are no more variables in there. So I've got a constant, which is 3/2. So again, strategy-wise, there's a lot to think of. This helps you, cut down the amount of techniques you need to know with limits. This should do just about every kind of problem you're going to run into when we do limits for AP Calculus in the exam. So make sure you have this one written down somewhere handy in your notes. You could highlight the first one if you like, but somewhere that come May when we're doing some review, you can find it easy. So if you want proof that the people who write the AP exams are mean, I don't know why they wouldn't just let you use this technique in the first place. It's not in the curriculum, and the only reason I can think it's not there is they want you to work harder. So there you go.
So we can't use this for AP?
No, you can. Of course you can. Limits, by the way, limits, I don't believe that there are any limits from previous written sections, you know? I don't think, I can't remember anything in a written where you'd have to show your work. So the limits that I know of are all on the multiple choice, which again, whatever technique you use, they're blind to it because they have no idea in the multiple choice. So anyways, let's try some with L'Hopital's rule. So we already did this one, but we'll just, this was 2e to the 2x over 1, which was 2 to the 1 over 1. So that was 2. Let's try the next one here. Don't lose sight of what you're doing. Some limits you don't apply unless you use the indeterminate form. So when I say don't lose sight of what you're doing, let's plug these in. Here, I'm going to have 2 times the natural log of 1 over 1 minus 1. So this would be 0 over 0. Now I know I can use L'Hopital's rule because it's one of our interesting forms. If this did not happen, you're on your own. You got to find a different way to get your answer because L'Hopital's rule only works for the interestings, the 0 over 0, infinity over infinity situations. So that means I can take this one, call it the limit as x goes to 1. This will be 2 times 1 over x. And this here will just be 1. So this is the limit as x goes to 1 of 2 over x. And now, when I try to substitute, there's no issues. It's just 2. Okay, in this situation, we have natural log x over x. Some of you might be able to look at that and use your reasoning skills. Can anybody think of what the answer is going to be ahead of time? 1. So natural log grows as quickly as x grows.
0.
So why 0? You're correct. Why 0? Because you guessed. When we get big enough and you're taking natural log of the number, it's way smaller than when you're just using the number itself. So we should expect a 0 here. But let's substitute. If we put in infinity, natural log of infinity is still going to be infinite. X is still going to be infinite. So we can use L'Hopital's rule. Okay, does L'Hopital's rule apply to the new limit, this one here? Can we use L'Hopital's rule if we're stuck? How come we can't? You're correct. It's not an indeterminate form. If I plugged in the number now for x, I'd have 1 over infinity. That is not part of the special cases that you have to think harder about. But we've dealt with this, right? If I have 1 pizza and I'm sharing it with 10 friends, you know, they get 1/10 of a slice. 100 friends, they get 100th. 1,000, they get 1,000th. Eventually, if I had an infinite amount of people to share that pizza with, you'd have nothing. You wouldn't get anything because just too much of it has been split up. So in this case, you can't use L'Hopital's rule, but you should get 0. Okay, so we'll try this here. Again, when you see this limit, you should first make sure you have an indeterminate form. So negative infinity squared is an infinite value. Then e to the negative x. If I put in negative infinity, that would be e to the infinity. The 2 negatives would cancel out. So yes, this is a question suitable for L'Hopital's rule. That means I'm going to have limit as x goes to negative infinity of 2x over negative e to the negative x. Okay, so we try it again, and what happens? Let's see. That's going to become negative infinity and negative infinity. So I still have an indeterminate form. That means I can use L'Hopital's rule again. So here's my first L'Hopital's rule. Let's go again. Limit as x goes to negative infinity is going to be 2 over e to the negative x. So this will be 2 over an infinite amount, which is 0. So any constant loses to infinity, it becomes 0. So you should have some appreciation, I hope, for just how complicated those limits would be without L'Hopital's rule, and how simple L'Hopital's rule can make it. So let's say you have these kind of limits. What happens here if I have 1 minus cos x over x squared? So far, so good. L'Hopital's rule applies. Let's use it. So that'll be sine of x over 2x. So the sine of x is 0 and a 0. So I still have an indeterminate form, one which I don't have an answer for. So we can use L'Hopital's rule yet again. And cosine, that'll be a 1. So this is negative 1 over 2. So I can just use the direct substitution. That limit would be negative a half. Okay, so don't give up. It may be like the last couple examples. If you had... Oops. Oh, just positive cos. Yes, sorry. It may be that you have to apply your L'Hopital's rule more than once when you are working through your example. Okay, here's kind of a different one to think about. If we substitute this in, this would be 0 times... Does anybody remember what happens to the natural log graph? Like, picture the graph. What is happening at 0? There's a key feature on that natural log graph, one that you're supposed to remember. Peeking at our graphing calculators. What happens to natural log at 0? It's not defined, but what's happening to the graph? I don't know what's wrong with your calculator. It's probably just not graphing. Something's not on that one. There should be some picture of it. Okay, there are very few graphs that you need to remember. The trig ones we did to death, so I'm not going to mention those, but you do need to remember those features. The only other two really are the natural log and the exponential graph. But what's happening here is there's an asymptote, right? So if we were to try and evaluate it, this is the situation we have, 0 times infinity. Which again should make you think, well, that's an interesting battle. I wonder who's going to win. Maybe not. Maybe only if you're a hardcore dork like me. But 0 times infinity, you think 0 times anything is 0. But what if it's an infinite number you have? Is 0 times infinite? That should bring up more of a question. So this is, again, another indeterminate form. So we can't really use L'Hopital's rule because that's not how L'Hopital's rule works. Does anybody have a brilliant suggestion? Maybe some way that we could make it look like L'Hopital's rule? Rewrite it, yeah. So do you have a suggestion for rewriting? You just read a little farther ahead. Well, that's smart too, right? Pardon me? Oh, okay. So you could do this, and the answer is yes. But you now have a completely different beast, one which will be probably worse to work with. Just because we've made that function a lot more complicated. In fact, L'Hopital's rule, one of the reasons, one of the things that's nice about it is we can actually get limits out of these weird numbers. Anyways, we're not going to go down that road. We're going to try and go a simpler road. And it's really just like this. I've got a zero and an infinity here. So why don't I try this? All I did was, instead of having x on top, I'll put 1 over x on the bottom. They're equivalent, and if you double check now, this will be an infinite. It's actually negative infinity, just in case anybody's wanting to correct me on that. You would be right. And then 1 over 0, that would be an infinite limit as well. So now we have an indeterminate form, which is suitable to L'Hopital's rule. We've rewritten it in a way that makes sense for L'Hopital's rule. So this would be the limit as x goes to 0 of 1 over x divided by negative 1 over x squared. So this, at this point, it helps to think a little bit through what we're doing, because if we just blindly we go, oh, look at that, it's an infinity over infinity, let's do L'Hopital's rule again. We're going to be at it for a very long time, right? Can anybody think of something that we should do to end some of this suffering? Yeah, let's simplify it. You have this really awful looking fraction. Before, what made life difficult was that we had a natural log and we had an x. Now that natural log is gone, let's see what happens. So I'm going to multiply both sides by x squared. And now I'll have the limit as x goes to 0 of x on top and negative 1 on the bottom. So this will just be the limit as x goes to 0 of negative x, which now has no more issues, no more problems. We can just substitute it in. The answer would be 0. So as I said before we started, I'll be clear to you guys, these are beyond the AP exam. However, within local calculus curriculum and the local universities, this is the level that it will go up to as far as having to rewrite something to apply L'Hopital's rule. That's the level of problem solving that's going to be expected next year from you when you're at, in the real world. But for your AP exam, it's going to be a technique that's suitable, and I don't know of times when it's not applicable the first time. Yes?
For the question we just did, is 1 divided by x to the 0 going to be 0?
1 divided, so this part right here, you're asking me about this?
Yes.
And when I put in x equals 0, and I should get infinity, right? So that was part of our infinite limit laws, like where we find vertical asymptotes. Any constant divided by 0 gives us a vertical asymptote because the limit is infinite, or does not exist, but it's infinite. Okay, good question. Okay, so here are some of the other interesting things where you might find L'Hopital's rule and you didn't know it. We just looked at 0 times infinity, 1 to the infinity, infinity to the 0, 0 to the 0, and infinity minus infinity. Those are all unusual situations, ones which might hopefully spark some curiosity to help you realize that L'Hopital's rule might be a strategy for you. Okay, so we're going to try doing some rewrites. Let's try a couple together just to make sure you're on the right track. First thing we're going to do is substitute. What will I get for the first piece in this product? E to the negative infinity is... I hope not. If you substitute in here e to the negative infinity, that's like, you could use some common sense and just, this is a very large negative exponent. So it's 0. But hopefully you don't have to reason that far. Hopefully you are able to just apply that very big negative exponent and know that it's going to be a 0. So we're not ready yet. We have 0 times infinity. We need to work this out. So see if you can figure out how to rewrite it so that L'Hopital's rule applies. Okay, so anyone have any luck that wants to share?
Go, Jim, go. Tony does.
So what did you, why don't you just get us started and I'll try and take us some of the way there too.
Root x over e to the x.
Sure, that sounds good. So limit as x goes to infinity, root x over e to the x. Now when I try, I'm going to have an infinity over infinity situation. So that means I'm able to apply L'Hopital's rule, and I'm going to have the, oops, excuse me. I'm going to have the limit as x goes to infinity. So 1 over 2 root x, and the bottom will be still e to the x. Okay. So this time, what do I get?
1 over 2 ex root x.
Okay. If we were to substitute, I just want to show you a couple ways of thinking about it, right? If I plug in the infinity, what happens to the top? Yeah, the top would be a 0, and the bottom would be infinity. So at this point, we should be able to stop because we have a constant and we're dividing it up an infinite number of times. So in this case, 0 divided by infinity is going to be 0. The other way you could do this when you rewrite it, that's the same as the limit as x goes to infinity. I'll just move this to the bottom. I'll get rid of that complex fraction. That's 1 over infinity, which is again 0. 1 loses out, and we should have 0 at the end of this. So again, keep some perspective here. These are very difficult L'Hopital's rules. This is not an indication of your advanced placement course anyways. This is just a preview to help you next year. So when we get to the next one, there has to be some creativity. But the creativity is something you already have seen and used, and you in fact did it with limits. Does anybody remember what happened with this kind of a limit? It's not always obvious, but what you're looking at here is causing problems because it's infinity minus infinity. It'd be really nice if we could collect the like terms. Then we would just have one value. Like if it was, infinity plus 5 times infinity, we could just, they'd be shoved together and be infinite. But here we can't do that because of the square root. We can't collect like terms. So one way that I could do this in order to make the like terms come together is, ideally I'd like this to happen. But I can't just do it to one of them. How do you get that difference of squares to happen? Do you remember?
Multiply.
Yeah, if we multiply in by the conjugate, then I'm going to have, I'll be able to combine my like terms. So this will be root x squared plus 6x plus x. And on the bottom now, root x squared plus 6x plus x again. So use the difference of squares pattern just to make the algebra go quicker. And this will be x squared plus 6x minus x squared. And on the bottom, I'm going to have root x squared plus 6x plus x. So I'll have 6x over root x squared plus 6x plus x. And in this case, when I substitute, the top is infinite, and the bottom that I've created is infinity plus infinity, which is just infinite. Infinity minus infinity is different because we don't know which one, you're taking away something. Did you take away more than you started with? Did you take away an amount that leaves a constant? It's harder to say, but when you're just adding two infinite numbers together, you get an infinity out of it. So at this point, I'm able to use L'Hopital's rule. The limit as x goes to infinity of 6 over 1 over 2 root x squared plus 6x. And I'm going to be multiplying it by 2x plus 6 for the chain rule. plus 1. And the reason I haven't collected my like terms yet is what I'm hoping is maybe I have something that I can work out now without having to do any more derivatives. It'll be a little easier for me to think about if I do one little piece of simplification here. I'm going to rewrite this as 2x plus 6 over 2 root x squared plus 6x. So, does anybody remember what happens to... Yeah, there's a factor of 2 there, but looking at that one... Sorry? Looking at this one here, you could keep doing your L'Hopital's rule, but let me just show you one thing. You couldn't do L'Hopital's rule because you have a 6 on top. But this is the piece, if I was to take a look at it, we're going to infinity, so we're going to use some Bill Gates style... hopefully I don't get a call from his lawyers one day that says, please stop mentioning Mr. Gates on YouTube. But anyways, we're doing some Bill Gates style of math, right? And basically what we'd be saying is, as we go to infinity, that's not important to me. Neither is that. The only one that's going to be significant are these pieces. So the significant pieces, 2x and 2x, that would go to 1. So I know this limit here is a 1. So I'd have 6 over 1 plus 1. So that's 3. Okay, for the purposes of not overkilling everything, depending on where you're headed next year, those of you who are fortunate, or I guess should I say unfortunate enough? Anyways, going towards engineering, physical sciences, the rest of the sheet would be applicable to you. However, I can tell by the some of the faces in the crowd right now that this is about the threshold that we're going to get to with L'Hopital's rule, and that's okay. For our course this year, the world that we're going to be living in with L'Hopital's rule is our first page of notes up to here. The intention I have with giving you L'Hopital's rule is now you have another strategy to help you with limits. So for our purposes, we're pausing. Just know that more is to come, I guess, in your future. But for now, you can count on our first page of notes. Okay?